Welcome. Thank you for coming to the last talk of the day. My name is Patrick Williams. I'm a software engineer at Meta, and I'm going to be talking about dbus, asynchronous dbus with C++ coroutines. So a little bit about me first. I'm a software engineer at Meta. I'm the tech lead for all OpenBMC work for all of our storage, compute, and AI systems. So we probably have one of the largest deployments in the world of open source BMCs. There's maybe one other company that might have more than us. So I also have been working on the OpenBMC project since the beginning. I took a little bit of a break, but I'm one of the primary maintainers of the project, and then some of the leadership organization I'm a member of. So I'm going to talk about kind of four sections here. What is OpenBMC? Can we generate dbus bindings? What are C++ coroutines? And then a bunch of code examples of what we've got in place. So what is OpenBMC? If you're not familiar with what BMC is, it stands for Baseboard Management Controller, which doesn't tell you a whole lot. But most servers in the world have an embedded Linux device that provides remote management. So you think of a server, when you roll it into a data center and it's on a rack, you plug it in, how do you tell it to turn on without somebody pushing the power button? Right? That's one of the things the BMC is responsible for. I've got on the right-hand side here kind of a toy example of a problem the BMC is responsible for solving, which is the fan control. So how do you keep your server from overheating? The BMC is responsible for that. So it kind of has a control loop where you're reading thermal sensors of various sorts, perhaps maybe voltage regulators, a bunch of metrics to figure out how much power is being consumed, how hot everything is, and then as a result you set the fans at some speed. So math happens. Those sensors, they can be I2C devices, that's pretty common, and then you use the HWMON subsystem. But they could also be, for instance, the NICs or the GPUs have thermal sensors that typically the BMC can get over a protocol called PLDM. You think of SSDs, they've got NVMe MI, so there's a bunch of different protocols that the BMC needs to talk to get something as simple as what temperature are all the devices. Another thing you got to think about with a BMC or a server is how do you remotely manage it? And so there's a number of standards. One is Redfish for managing your server. And so there's actually Redfish APIs for maybe applying a different thermal profile. For instance, maybe you want to go into a performance mode or a power save mode. You could do that over Redfish, and then the BMC needs to apply a different fan table responsible for that. So those are the kinds of problems that the BMC is responsible for. The implementation we have is called OpenBMC. It started in 2015. And there are a number of now commercial and hyperscale deployments of it. So there's some big tech companies that all work together on it. It's built on top of Yocto Linux. So the internals, how do you, I mentioned like thermal sensors, you want those to be replaceable entities. How do you do that? We use dbus as the underlying architecture for all the software inside of OpenBMC. That allows you to replace or add new components based on your hardware, and then different other pieces of code within the BMC can interact with those dbus objects and get the data they need. And it happens that if you go look at the OpenBMC organization on GitHub, you'll see there's probably like 100 different code repositories because there's a bunch of small little pieces that do kind of one thing. Maybe they expose one dbus object, and that's all they do. So now going a little bit deeper, we have a library that we wrote called Sdbusplus. It's a C++ binding for dbus. Most of the code in the OpenBMC community is written in C++, and for people that don't like C++, you're probably thinking why, but there's some just legacy there. Rust, we wrote it in 2015. Rust wasn't even a thing really that people were talking about, so I think if we started today, probably we would switch to Rust. But so GitHub repository for it there. Some of the things that it supports, right? All the usual stuff in dbus if you're familiar with that, but kind of modern C++ wrappers around it. So resource acquisition is initialization as a common pattern in C++. It means when you create a variable, if that variable goes out of scope, you automatically release things. So there's kind of those wrappers around connections, messages, slots, all those things that are in dbus. It also has type deduced interfaces for message packing and unpacking, and I'll show a little bit of a demo of that later. But for instance, if you wanted to send a C++ vector over dbus, you can just push that into a message and the library does the right thing. It takes whatever your container structure is and turns it into the array in dbus and fills up the array and sends it in the message. And then there's three different ways we have for doing dbus clients and servers, and that's partially just because of technology changing over the years. So the new one that I'm talking about today is C++ coroutines. So dbus bindings. One of the things that we do is I mentioned we've got about 100 different code repositories, and those need to talk to each other. And ideally, we have to kind of document those dbus interfaces, but on top of that, ideally, the compiler can tell us if we've done it wrong. And so what we like to do is we have a interface YAML that documents dbus interfaces, and then we have a generator that can generate bindings against those YAMLs for the C++ language to interact with. So if someone were to change a dbus binding or add a new interface, the compiler will identify that for us. So the YAML format that we have has support for dbus properties, methods, signals, and errors. And then on top of that, we have a couple extensions. One of those is the enumerations. So a common practice is to use a C or C++ enumeration, and we actually turn that into a magic string as it goes across the dbus. So from a programming standpoint, you can use C enums, but when it goes across the dbus, it goes into a portable schema. So example here is our sensor interface, or our sensor value interface. So I talked about thermal sensors. Sensors could also be the fan speed, so RPMs. There's a bunch of these units along the right-hand side. But a sensor has a value. What is the current reading of the sensor? It has a range, so a max value and a minimum value, and then a unit associated with it. And then there's other interfaces, for instance, like thresholds. Maybe some sensors have thresholds, some don't. Those are all handled by a different interface. So next, what are coroutines? So asynchronous dbus in C, which is what you may have to do if you're writing the C language, there's a function called Sdbus call method async. And you can see the list of parameters you have to give there is quite extensive to make a asynchronous dbus call. And one of the things you have to do is pass in the continuation function, what do you want to do when you get the async response back. So in order to create an async method, you kind of have to figure out what all the state is that you want, maybe pack that into some structure. You've got to pass this callback method, so you kind of split your function across multiple C routines. And that's affectionately called callback hell if you've done any kind of asynchronous programming in typical frameworks. So if you think about, I made a simple example here of just calling the systemd manager to figure out what architecture we're running on, and that alone is, a full screen of code. So think of an external interface like Redfish, where you're getting a JSON request, and then you have to call maybe 20 different dbus objects to collect the data you need to figure out the response there. And you want to do those all asynchronously so that you're talking to all those different daemons in parallel. How do you do all that in a manageable way? So enter C++ coroutines. So wouldn't it be great if the compiler could generate the callbacks for us, and we can kind of shove it all into one C++ function or C function and have the compiler generate all the state that goes between the callbacks and preserve it for us without us having to do that manually. And that's exactly what C++ coroutines do. If you're familiar with asynchronous programming in, for instance, Python or Rust, it's called async in both of those. So you have two keywords, which is async and await, in both Python and Rust. And C++ has kind of the exact same behavior. They had to use the word co-await and co-return, but other than that, if you're familiar with asynchronous programming in those languages, it's almost identical. So that was introduced in, I believe, C++ 20, but that was the definition of what a compiler should do when seeing these keywords, but the standard never defined what is a task, which is kind of important for doing asynchronous programming. That's hopefully coming in C++ 26. There's a bunch of developers that are currently at NVIDIA that are working on a library that's called Sdbusplus. And Eric Niebler is one of the main developers there. He's done a bunch of talks on asynchronous programming. So if it's something that's interesting to you, he can go search his name and you'll find probably 6 different talks that are all great. So I've got code here on the screen. You can see what this is doing is it's a function that's exactly identical to our C function before. It's looking up, it's creating what I call a proxy over to the system manager. So you can see we have well-named parameters instead of just some string embedded in the third parameter or something like that. But you can see the service, the path, the interface. So those create your proxy over to a remote object. And then I want to read the architecture property, and we know that that's a string. And so we can call systemd.getProperty with the architecture, and we can co-await on that. What that means is that when our code gets to this point, it's going to do the dbus magic to go over to that other process, and then the compiler is going to have put in magic to suspend this code until the dbus callback comes back, and then through compiler magic it will then resume. So then you can think of it as we have a message back from the dbus server in response that has in it a string, we believe, and then we can unpack that string, return it, and then in this case store it into a variable. Okay. Hopefully that all makes sense. So what do we get with this, right? There's no more callback hell. If you've got 20 different dbus calls that you want to do, you can just do them all in sequence. It's very readable, straight line. And then on top of that, we get a lot better ergonomics. So we have a C++ type system that gives you, compile time checking of all of these things. And then hopefully people agree, but I think it's much more concise and clear as to what's going on rather than 8+ parameters to the Sdbus, or the Sdbus function. On top of that, we get some amount of compiler safety here. And in the library, we can get runtime safety. So for instance, as a programmer, I put standard string here saying that the architecture property, I think, is a string. If it wasn't a string, I made a mistake, that we get runtime safety, and that the underlying library here will see that it's not a string that I got back from the systemd manager, and it'll throw an exception. If for some reason the arc property that I have here can't store a string, then the compiler will yell at us. All right, so now we're going to get into some code examples. If you want, I put all the examples in this repository. The slides are all available already. You can go look at them. But okay, so since I work for Meta, we own Facebook, and if you're familiar with Facebook, there's something called the poke. So I defined a poke in dbus. So on the right-hand side, you can kind of see what I've defined. I've got a property, which is the last poke, and then I've got a method, which is the poke method. I've got a source, or maybe you think of it as a username or something like that. And so when you call this dbus method, the expectation is you give it a string, which is the user that poked, and you get back how many times that user has poked this interface. And then as a side effect, the last poke gets updated. So we can define this YAML in com/meta/poke.interface, and then in the Sdbusplus library, there's a Python script that you can run which will generate the server and client bindings from that YAML. So it will generate a common header file, a client header file, and what's currently called a server header, because there was already server for the synchronous ones. So this is asynchronous. And it can also generate Meson snippets for you to kind of hook this all into your repository if you're using Meson. All right, what does a client library or client look like that uses these bindings? So like I said, Sdbusplus generates a class, which is client com meta poke, and in it, it has generated functions for all the get and set properties, for method calls, and then I'd like to generate, I don't have these done yet, but a get all and a signal watch generator. The functions that generated are all type safe based on the YAML. So going back to the YAML, we've got the types here like string, size, so an integer. Those are all, it makes sure that everything is type safe. And then because of it being co-await, there's actually ways in the library that you could do kind of scatter-gather operations. So I could spawn off a bunch of coroutines into an async scope, it's called, and then I could await on that async scope. So the code here is showing a client function called multipoke that you give it a set or a vector, if you will, of a bunch of users. And what it does is just in sequence goes and calls the dbus server for this interface and calls the poke interface over and over until we've exhausted the vector. All right. Next up, servers. It also generates classes that you can inherit from for the server. It generates those. You can overload certain method calls, so certain methods, such as method call, get property, set property, to overload certain behavior that you want in your particular implementation. Also, for the properties, if you don't have any special behavior, you just have some raw vanilla type, it will give you that for free if you decide not to overload. And then I guess it also has methods for generating signals as well. If you're not familiar with C++, there's kind of two tricks in here in this code if you were looking at it. One is something called tag dispatch, and the other is called the curiously recurring template pattern, CRTP. So you can see this class here. The class itself is passed into a template. That's the curiously recurring template pro pattern, sorry. And so that allows the generated class to introspect the implementation class that you have provided, so that it can figure out what methods did you overload and which ones did you not. And so then the next function here, you see this method call, and you see the first parameter to it is poke. This is something that's called a tag in tag dispatch. And so this allows, again, kind of the introspection through overloading to kind of deduce what your implementation did without having to rely on like C++ virtual everywhere, which has performance penalties and size penalties. So this example here, you can see I've implemented the poke method. And what that does is you can see it first just updates the last poke variable, and then it also updates a map that just keeps the counts for us, and then also returns the most recent count of the most recent count here. It also overloads the property, the set property for poke, and then I just did some magic which says only root is allowed to call that property update for some reason. So. If for some reason it wasn't root, you see that we have actually an error that can be thrown, and those kind of flow across the dbus with the normal dbus error methods. You can also make, this method call here is listed as async, so it could do something interesting where it actually did, inside of itself, it could do a co-wait on something else. For instance, maybe in order to satisfy this method call, the code needs to turn around and call another dbus daemon, and you want to kind of free up the daemon to do other things. You can do a co-wait in here, and it will suspend and then resume. If you want it to be non-async, you see that the return type is this task. It could just be the return type directly, and then the class will become non-asynchronous, or the particular method will become non-asynchronous. So what's next from an implementation standpoint? I kind of mentioned already, there's a couple enhancements that I'd like to get done, such as the get all and then signal matches. We have quite a bit of existing OpenBMC applications that are using non-asynchronous code. I mentioned that we had that before, and then a bunch of people had kind of written some handwritten boost ASIO daemons within OpenBMC, and I'd like to get those all refactored to kind of have a consistent implementation. And then, I'd love to see other projects, if you're doing dbus in C++, kind of take advantage of this. The one caveat is we always keep pretty up to date in the OpenBMC community. So we're currently needing GCC 13 or later, and C++ 23. That's kind of the first compiler where C++ 23 is pretty solid. So with that, any questions?
So thanks for the talk. Maybe I have two related questions. So you said that application is OpenBMC, and you spoke about fan control and temperature. Previously, we saw some pictures of a melted PCI card. So does this application does it have real-time requirements or some requirements like this? So that's the first question. Second, this asynchronous code, is it deterministic? For example, if you invoke more calls in parallel, so is defined which will be evaluated first, the return value? So is there determinism? Thank you.
Yeah, great question. So generally, BMCs do not have real-time requirements. Generally, if you have real-time requirements, you usually have, in most servers, there'll be like CPLDs or particular dedicated hardware to deal with real-time requirements. So an example I've seen a pretty common server design is that the heartbeat from the BMC, so there's a watchdog within the BMC, and that emits kind of a heartbeat signal. If the watchdog isn't poked within the BMC, that will signal the fan controller hardware to say the BMC disappeared, and then the fan controller will usually kick the fans into max speeds. So generally, BMCs don't tend to have real-time requirements. Your second question was kind of the determinism here. And while this is async, it's not multi-threaded, right? So it's slightly different. So anytime you have a co-await, it will, think of it like a stack. Like your function gets paused right there, and the compiler creates a stack, and it switches to think of it like switching to another stack. And so it kind of calls some framework code to say, this task has hit a suspend point. What should I run next? So it's almost more like cooperative multi-threading on some really old operating systems rather than the name is escaping me. Non-cooperative multi-threading.
Preemptive.
Preemptive. Thank you. Yes. It's deterministic in the sense of when you hit a suspend point, your code pauses and then it resumes whenever whatever you co-awaited on is available.
Mm-hmm. Thanks.
Yeah.
Hi. Hi. First of all, I love it. Thanks so much for the talk. Very likely to use this. Just so happens that I'm working on something called iFix, which happens to be a YAML-based IDL that generates dbus bindings. So it's right up my alley. I'd like to talk to you later about it. To the question, have I understood correctly that you're not implementing a server like dbus daemon or dbus proxy? This is simply only a library that generates dbus messages, right? Or did I misunderstand?
I'm not quite sure if I understand you correctly, but so in the examples, there's actually a server CPP, and that will generate the full daemon for you. But okay. One of the things that the library has, you'll see the first parameter here is the context, and that is the asynchronous context under which all of your coroutines are running.
But it is client-server point-to-point, as opposed to having like a dbus broker separate process channels message, which you probably could do, of course. But
right. So we rely on the system dbus broker.
Yeah. Okay. Is there anyone else? Otherwise, I have one more question.
You have 1 minute left.
Okay, just so I understand, you are providing the source code to the standard task?
Yes,
Or-
we can, yes. So currently I import it because they don't have a great way to integrate it with Meson. The hope is that that team is planning on it being part of the C++ 26 standard, and so.
Yeah, but until then, I'm just trying to figure out how to.
So currently it's not an extra dependency that you have to pick
Right.
up. It's
And
put
that
in
all
the library.
compiles will C++ 23, you said?
Yeah.
Okay,
Yep.
thank you.
Yeah, you're welcome. Nope.
All right, that's it for this room, and I think for day 2 sessions in the Dome. Please feel free to go to the main hall after this, where Chris will conclude the conference. Yeah?